Hi, I'm John Doherty, and this is another in our series of videos on the nuts and bolts of using PEST and PEST++. Today we focus on PL-Proc, which actually is the subject of another video in this series. We look at two issues which we blend into one model domain: new ways to use pilot points and spline-based representation of alluvial channels. Now, if you like this video, if you like the contents of this video, you can do everything that we talk about if you download a tutorial from the GMDSI website on the same subject. Everything we talk about in this video is done in the tutorial and more. So if we're going to, first we'll talk about new ways to use pilot points. We'll talk about the concepts and then how to implement those concepts. So as we go through this video, that's the way we'll do it. We'll talk about concepts and then implementation details. Before we talk about new ways to use pilot points, we'll just briefly discuss the traditional way to use pilot points. We start off with a model grid. Now we've got a very simple model grid here, a simple structured model grid. Note, however, that nothing I talk about is restricted to the use of structured model grid. Everything we talk about we can also do just as easily with unstructured grids. We're going to talk about a simple regular array of pilot points. Everything I talk about can be done just as easily with an irregular array of pilot points, with the spatial density of those pilot points varying from place to place throughout the model domain. So in the traditional way of using pilot points, we assign values to each pilot point, hydraulic property values, because we want to end up with a hydraulic property field that populates this model grid. So we assign hydraulic property values to each one of these pilot points. And then we interpolate those hydraulic property values to the model grid. PL-Proc supports a variety of ways to undertake spatial interpolation. They include kriging, radial basis functions, and other options. Interpolation can be simple or sophisticated. In more sophisticated ways, the interpolation process can take account of spatial anisotropy of correlation lengths of hydraulic properties. And that anisotropy can vary in different parts of the model domain. This can all be taken care of using functions such as calc kriging factors auto 2D from PL-Proc, which we'll see again later in this video. When we use pilot points, however, we have to use a covariance matrix as well. So we assign hydraulic property values to the pilot points, we interpolate to the model domain, and then we're going to use these interpolated values, or use the parameter values that we assign to the pilot points in to do a variety of different tasks. Principal among which are calibration if we're using PEST, or perhaps ensemble based inversion if we're using PEST PPIES. In either case, we need a covariance matrix to go with our pilot points. If we're doing regularized inversion, that is calibration, that covariance matrix will need to express, it's used for regularization. If we're using PEST PPIES, the covariance matrix is used to generate random realizations of the hydraulic property values that we assign to the pilot points. This is necessary because there's spatial correlation between these hydraulic property values, and that needs to be expressed in random field generation and in regularization. And in many model areas there could be anisotropy of spatial correlation, different correlation lengths in different directions. Or there could be different variances of hydraulic property variability in different places within the model domain. That needs to be expressed in the covariance matrix. So the covariance matrix that goes with our pilot points may end up being somewhat sophisticated. Utilities supplied with the PEST suite and PL-Proc itself give you the ability to create quite sophisticated covariance matrices to handle these kinds of situations. Note, however, that this all starts to get a bit painful. It's all doable, but handling these covariance matrices that specify complicated geostatistics does become a little painful. but it may be necessary in environments, in model domains in which hydraulic property geostatistics of hydraulic property variability is different in different parts of the model domain. And that happens in a lot of places. Okay, that's the traditional way to use pilot points. Now let's look at the new way, or the alternative way. In this case, instead of assigning hydraulic property values to these pilot points, we assign IIDs to the pilot points. Now, what's an IID? An IID is a statistical term. It's an independent and identically distributed random variable, or in our case, a random normal deviate. It's got a mean of 0 and a standard deviation of 1. We assign one of these to each of these pilot points, and these are completely independent of each other. So the things that we're assigning to pilot points now are not spatially correlated. They're independent normal deviates. No need for a covariance matrix. But our task at the end of the day is to populate this model grid with a hydraulic property field which shows exhibits the geostatistical characteristics that we would like it to have. Spatial correlation, possibly with anisotropy, possibly with anisotropy which is different in different parts of the model domain, possibly with a degree of variability which is different in different parts of the model domain. So to go from our pilot points, which have IIDs associated with them, to a model grid in which we have a hydraulic property field that has the geostatistical characteristics that we want, we undertake spatial averaging of the IIDs that we assign to the pilot points. So all the pilot points have IIDs. Suppose we want to assign a hydraulic property value to this cell of the model grid. Then we sum the values of these IIDs with a weight. That is, spatial integration, spatial summation, but it's weighted spatial summation. The weighting function decays with distance from the point to which we're assigning a hydraulic property value. The nature of this weighting function determines the geostatistics of the hydraulic property field that we end up with. The variables, the parameters which govern the nature of this weighting function I'm referring to herein in this video as geostatistical hyperparameters. So the geostatistical hyperparameters which describe this weighting kernel can be the same all through the model domain, in which case we generate a hydraulic property field which is stationary. Or the geostatistical hyperparameters pertaining to this kernel can vary from place to place, in which case the hydraulic property field that I end up with in the model domain is described by non-stationary geostatistics. And this is done by having a different kernel operative in different parts of the model domain. This kernel can be continuously variable in all the different cells which occupy the model domain. Collectively then, I do my spatial integration and end up with a spatially correlated hydraulic property field. Now the benefits of doing things this way, there's a couple. Firstly, I do not have to undertake spatial interpolation from the pilot points to the model grid. So the necessity to come up with a means of doing spatial integration, taking into account possibly anisotropy that varies from place to place within the model domain, I don't have to do that anymore. Secondly, because the variables that I'm associating with each one of these pilot points is independent of each other, I don't need a covariance matrix anymore. So they're the good things. I do, however, have the responsibility of ensuring that hyperparameters are assigned to each cell of this model domain. These can be the same if we want to end up with a stationary hydraulic property field. However, they'll be different and spatially variable themselves if we want to end up with a non-stationary hydraulic property field. So I have to interpolate the geostatistical hyperparameters to all the cells of the model grid. I can interpolate from so-called conceptual points, which is the subject of another video. These are just pilot points, probably further apart than normal pilot points, which host the values for the geostatistical hyperparameters. Or I can assign the geostatistical hyperparameters to the pilot points. Or they can be assigned using zones based on geology. Either way, all cells within this model domain have to have the hyperparameters required to construct the local kernel. The take-home message here, though, is that these IIDs, which are assigned to the pilot points, they take care of where the heterogeneity is within the model domain. The hyperparameters that affect the kernel and the kernel itself, that takes care of the nature, the patterns in which that heterogeneity expresses itself in different parts of the model domain. Okay, they're the concepts. Now let us look at some of the implementation details. So here's our model grid. Now recall from another video in this series that PLProc works with entities, principal among which are C-lists, P-lists and S-list. A C-list contains a list of coordinates. P-lists and S-lists associate numbers with those coordinates. As we said before, our model grid is structured. PLProc can obtain the wherewithal to assign a coordinate to each one of the centers of this structured model grid just by reading a structured grid specification file. Here's the function, read mf grid specs, and here's a structured grid specification file. It's particularly easy, the grid specification file for a structured grid. The specification file for an unstructured grid can be more complicated. PLProc can read those too. So by using this function, PLProc has assigned a coordinate to the center of every cell of the model grid. Pilot points can be read from a pilot points file, a text file. We have the names of the pilot points, their coordinates, and in this case we're associating geostatistical hyperparameters with the pilot points. We have the mean value of the hydraulic property that we're going to generate realizations of in the model domain. We've got the bearing, the range, the anisotropy, the sill. So we've got geostatistical hyperparameters that exhibit spatial anisotropy and that are variable throughout the model domain. Pilot point data, the coordinates and associated variables that are associated with each of the pilot points, can be read using the read list file function from PLProc. PLProc then generates a C list containing pilot point coordinates and associated P lists holding pilot point associated variables. So now we've got the coordinates of all grid cell centers read by PLProc. We have all the pilot point data read by PLProc. Our next task is to undertake spatial interpolation of the geostatistical hyperparameters to the model grid. This is easily done using Calc Kriging Factors Auto 2D. Even though we've got spatially varying anisotropy in this model domain, these pilot points are close together that we can use simple isotropic Kriging to undertake the spatial interpolation from the pilot points to the model grid of the geostatistical hyperparameters. We calculate Kriging factors, then we actually implement the Kriging of those geostatistical hyperparameters from pilot points to the model grid. Now come the IIDs. Now there's a couple of options here. In this video we're generating random numbers. We're going to generate random realizations of hydraulic property fields and also of the locations and properties of alluvial channels, but we could also read in IIDs if, for example, these IIDs were being adjusted by PEST or PEST++. That's discussed in the tutorial that I spoke about at the beginning of this video. In the present case, we're generating random realizations and we're doing it all within PLProc. So now we're going to use the gen_rand plist basic function provided by PLProc to generate random values of IIDs at each one of these pilot points. Random number generation is easy, there's no covariance matrix. By definition, IIDs are completely independent of each other. So we generate random realizations of the IIDs. And then we use function spatial average 2D to undertake spatial averaging, weighted spatial averaging of these IIDs in order to construct a hydraulic property field for the model, a hydraulic property field that has the spatially varying geostatistics that we desire. In this case, our kernel function is going to be of the power type, so it has a certain value at each cell to which we're assigning a hydraulic property, and that value decays with distance from the cell. We're using a power of 1. Now, PLProc provides a lot of options for the kernel that we can use. In the end, we just choose the option that gives us the hydraulic property fields that look like what we want to look like, that have the patterns that we want and the spatial correlation lengths that we want. So, in the present case, we generate realizations of hydraulic property fields to populate the model domain. I'm just going to generate 5. You can see that we have anisotropy of hydraulic properties within the model domain. You can see that anisotropy is different in different parts of the model domain. So here are some realizations of the hydraulic property field that we just generated, and you can see that it exhibits spatially varying anisotropy. Our next task, if we want, is to write these hydraulic property fields to model input files. This can be done using the write model input file function supported by PLProc. So now we've populated the model grid. Our next task is to introduce alluvial channels to the model grid. We've populated the model grid with background hydraulic properties. Now the alluvial channels are going to permeate, intersect, travel through that model domain, and those alluvial channels are going to have their own hydraulic properties. That's what we'll look at next. So the first thing that we do is we introduce these things, which I'm going to call alluvial channel skeletons, to the model domain. As you can see from this picture, these are simple segments, polylinear features. We're going to have 2 of them in our model domain. They're defined by vertices, and these vertices are joined by straight lines. Now, these vertices serve 2 roles. Firstly, vertices joined by straight lines tell us where these alluvial channel skeleton segments are. Secondly, we can assign values to these vertices. In this case, we're going to assign geostatistical hyperparameters to these vertices. But these geostatistical hyperparameters will be describing not the geostatistics of the background material, which we've already dealt with, the host material. They're going to describe the geostatistical properties of the alluvium. And the alluvium is going to have spatially correlated hydraulic property field. The correlation length, the variability, the mean can vary from point to point, so the hyperparameters that we associate with each of these vertices can be different for each vertex. Then we're going to allow for the fact that we may not know exactly where these old alluvial channels are, so we need to be able to move them or generate random realizations of where they are. So we're going to introduce sliders. Now in PLProc, sliders can be quite complex, but in this case our sliders will be simply a line defined by its endpoints. So we have alluvial channel skeleton, and the vertices of that skeleton can move along sliders. The position of each vertex on its slider is described by a number between 0 and 1. The next step is to join those vertices by a spline. Now, we've got a spline-based curve here. In the background, actually this is a polylinear curve with 200 vertices. We just can't see the fact that it's polylinear because the segments are so small. that number 200 is user selectable. Could be more, could be less. But the point is, here we've got a nice sinuous channel. Well, it looks like a channel because it's a nice sinuous curve that is connected to the skeleton at the vertices of the skeleton. Now, when we construct this spline-based curve, PL-Proc does more than just construct the spline. It can also undertake spatial interpolation of variables that are assigned to these vertices down the spline. So, we create a spline and we interpolate the geostatistical hyperparameters down the spline at the same time. So, our alluvial channels have continuously varying geostatistical hyperparameters along their length. They're the concepts. Now let's look at the implementation details. Once again, simple text files. Here we've got a text file in which we have the coordinates of every vertex of our alluvial skeleton. Integer denotes whether we're looking at the left or the right hand skeleton. Remember, we've got two skeletons which permeate our model domain. Here are the geostatistical hyperparameters: SIL, correlation length, mean value of the hydraulic property. Note that these vary from vertex to vertex, so our alluvium, like our host material, is going to be characterized by spatially variable geostatistics. We use the simple read list file PL-Proc function to create a C-list based on these vertices and accompanying P-lists that hold the hyperparameters. So now our alluvial skeleton is known to PL-Proc. Our next task is to read the locations of the sliders. Recall that each slider is just a simple straight line defined by the coordinates of its endpoints. So another C-list, and this column here just relates each slider to an alluvial channel skeleton vertex. Function read list file again allows us to read in slider positions. So now our sliders are known to PL-Proc. Now we have to place each one of these vertices on its slider. Now we could read in these positions if we wanted to, but in this video we generate everything as random numbers within PL-Proc. Everything is random number generation within PL-Proc. But alternatively, as the tutorial that I spoke about earlier demonstrates, we could read in these slider positions if we wanted to. In this case, we're going to generate random realizations of vertex positions on the slider. So we use gen ran plist basic to generate random numbers, uniform distribution between 0 and 1 for the position of each one of these vertices along its respective slider. And once we've generated positions of the vertices on their sliders, we simply use function slide CList vertices on CList to attach that the vertex to the slider for all the vertices and all the sliders. And if we do that multiple times, we've got, in this case, 5 alluvial channel skeletons permeating our model domain, with each realization having different locations of the vertices on its respective slider. The next task is to turn this skeleton into a nice sinuous curve that looks like an alluvial channel. For this we use PL-Proc function structural overlay to spline. So structural overlay to spline gives us this nice sinuous channel, and it also, as I said before, undertakes spatial interpolation of hyperparameters associated with vertices down the spline. So at this stage now, we not only have splines, but we have hyperparameters, geostatistical hyperparameters, interpolated down to all the 200 micro vertices of these alluvial channels. 200, could be more, could be less, that's our choice. So now we associate a spline with each one of those alluvial channel skeletons that we had before. Each one of them now has an associated spline, so that collectively we have 5 realizations of our alluvial channels which permeate our model domain. Now that we have our alluvial channels in place, we need to populate them with random hydraulic property fields. Now recall that these alluvial channels have 200 micro vertices associated with them. That 200 is user selectable. Now there are a number of ways to do what happens next. Each has its advantages and disadvantages. We're going to use a similar method for generating hydraulic property realizations down these alluvial channels, a similar method to what we did before for the background hydraulic property field. So here are some of the vertices along our alluvial channel. We're going to generate random realizations of IIDs and associate them with these vertices. Now we could generate them internally. We could read them from outside if they were being written by PEST or PEST++ during a parameter adjustment process. In this video, as I said before, we're generating everything internally to PLProc. So we generate random numbers, IIDs, random normal variates, mean of 0, standard deviation of 1, and we assign a random number to each one of these micro vertices. Then we undertake spatial interpolation. We undertake spatial averaging with a averaging kernel here, which determines the geostatistical properties of the material which populates these alluvial channels. Recall that the hyperparameters which govern the shape of this kernel were interpolated from the vertices of the original alluvial skeleton. So, just to try to demonstrate what's happening here, suppose we wish to assign a random hydraulic property to this particular vertex, this particular micro vertex of the alluvial channel. The spatial integration process looks a little bit like this, here and here and here and here. After we've done this for each of these micro vertices, we end up assigning to each micro vertex a hydraulic property value. Collectively, the geostatistical description of the hydraulic property distribution along the alluvial channel is in accordance with the hyperparameters that we used in the spatial averaging kernel. So now we have hydraulic properties with the geostatistics that we want assigned to all parts of these alluvial channels. They're the concepts. Now the implementation details. To generate random realizations of IIDs, gen rand plist basic once again. So this is an easy process. We now have an IID associated with each of these vertices along each of these alluvial channels. Spatial averaging, once again, function spatial average 2D. We do it once for the left channel, once for the right channel. So that now, at each of these IIDs, we have a hydraulic property value. Collectively, the geostatistics of the hydraulic property distribution along these alluvial channels is what we want, as defined by the hyperparameters that we ascribed to the vertices of the original alluvial skeletal segments. So now we've got alluvial channels in place. Those alluvial channels are populated with hydraulic properties. Our next task is to blend the hydraulic properties of the alluvial channel with those of the background host material. So here's the way it works. Here's our alluvial channel represented by a spline with a whole lot of micro vertices along the channel. Each one of these micro vertices has a hydraulic property assigned to it. Along that cross section, here's the underlying model grid. Now, close to the alluvial channel, with a width defined by the alluvial channel width, which we can assign as part of this process and which can vary along the channel if you like. Close to that channel, hydraulic properties of the underlying model grid are the same as those of the closest point on the channel. Further away from the alluvial channel, hydraulic properties of the underlying model grid retain their original values, the host hydraulic properties. Between the two, there is a blending operation, a decay function. This is described by a Gaussian curve. So what we have here is hydraulic properties associated with alluvium assigned to these cells, background hydraulic properties assigned to these distant cells, and intermediate values assigned to intermediate cells. Now there's a reason why we do it in this way, where we do it as a blending operation rather than as a discontinuous change of properties when we come to the edge of the alluvium. When we're doing inversion, when we're doing history matching, we want model outputs to be continuous with respect to adjustable parameters. If some of the parameters that we're adjusting are in fact the locations of the alluvial channel, then we want that continuity to be maintained as the channel position changes. By having a gradational change here rather than a sharp change, we maintain continuity of model outputs with respect to parameters as the locations of these vertices of the underlying alluvial skeleton changes. So the location of the alluvium can be an adjustable parameter, and continuity of model outputs with respect to those parameters is maintained. They're the concepts. Now the implementation details. So we use calc structural overlay factors to calculate factors by which this blending operation takes place. Function calc structural overlay factors actually calculates factors through which these hydraulic properties can be interpolated down their polylinear segments and then blended with the hydraulic properties of the background model grid. This is a linear operation. It can be done using factors. So we call function calc structural overlay factors first to calculate those factors. So now we have the wherewithal to do the things we need to do, interpolate these properties down the alluvial channel and then blend them with the background properties. The next task is to call function interpolate and blend using file to actually implement that interpolation process down the spline and the blending operation with the hydraulic properties of the host material. So there now is our model grid populated. We do this, in this case, 5 different times. In each case we have a different realization of the background hydraulic properties. We did that earlier in the video. A different realization of the alluvial channel hydraulic properties. We've just done that. And different locations of these alluvial channels. Once we have our realizations, we've populated our model grid, we can write model input files using plproc function write model input file. So what's the good of all this? Well, we have the means now to populate a model domain with complex realizations of hydraulic properties that can fairly realistically, I hope, represent at least some hydrogeological context of interest. Everything we talked about so far is based on a single property type in a single model layer. This is easily extended to multiple property types and multiple layers. So we can generate random realizations of host material, alluvial channel properties, locations of alluvial channels, and even geostatistical hyperparameters if we're not exactly sure what they are. And we're never exactly sure what they are. So we can give full voice to uncertainty, give full voice to our lack of knowledge of what happens under the grounds when we're undertaking many model runs to support, for example, data space inversion. As is discussed in other videos, data space inversion allows us to link the measured past to the managed future based on a few hundred model runs, based on realizations of hydraulic property fields. We can generate realizations of what have happened in the past, link them to what will happen in the future with a statistical model, and then condition our prediction of what will happen in the future based on actual field measurements. So generating complex hydraulic property fields becomes fairly simple. We just use IIDs and then undertake spatial integration for the background, the host hydraulic properties, the alluvial hydraulic properties. The locations of the alluvial channels are just uniform random variables with stretching from 0 to 1, and we can assign simple hydraulic property distributions to our hyperparameters. There's not a covariance matrix in sight. The random number generation required to produce fairly sophisticated hydraulic property fields for a model becomes a fairly easy process. Once we've generated random realizations of these hydraulic properties, they can be adjusted using PES-PP-IES. In this case, the values of the random variables are provided to PL-Proc from outside, and PL-Proc just undertakes the spatial integration, the moving of the alluvial channels and other things like that. We can calibrate a model using PEST-HP. Same principles apply. In this case, PEST-HP is providing the values for the IIDs, the locations of the alluvial channel segments on their vertices, on their sliders, etc., and the values of the hyperparameters. However, not a covariance matrix in sight. Yet again, regularization is easy. And finally, we could use ENSI, ensemble space inversion, to do the history matching. This is particularly suited for ENSI. So, for example, background property realizations could be placed into a number of realization groups and separated from realization groups that we're using for alluvial property realizations. Another realization group could host locations of the sliders, of the vertices on their sliders, so we can move those alluvial channels. And perhaps hyperparameters, if we're adjusting them, they don't need to be assigned to a realization group. They can be non-realization parameters. So I think there are abundant uses for what we've just talked about in this video. For more details, see the GMDSI tutorial that I mentioned at the beginning of this video. And with that, we conclude this video, and thanks for watching.